Since my first paper was a theoretical paper with a single. I think you just of the patients. But now it's the idea it's just a
Sorry, I should find yesterday. So young, young.
I am old. No, see, I'm not, it's like a random effect for the state, a random effect for the national state. And for the ventilation, like by how ventilation.
Great start.
Wait a minute, there are also people online, as you see, so realize that.
No.
Are you still running?
I am, yeah. Now, for me, I'm cycling. Because running is the temporarily. I got to work.
You gotta go run?
That's
That's
fine.
Hey, you can help where I was.
I do it once in the middle sleep.
Yeah. That's it. But everybody around now is on about it.
Yeah, I can do one in October again. Yeah, so that's many people attempting it and not well. Yes.
19 people online, so welcome. 19. Might still be people dropping. Welcome, Julius. For the people who don't know Julius, and I see most of the old generation, they know Julius very well because he worked for ABG. And actually, it's about 28 years ago you went to Australia. And why do I know 28 years? Because that's the time I've been working for ABG. When Julius left, I came. So that's why I remember that. So he's been working in Armadale. A lot of people know him from his selection index, Excel spreadsheet, MT index. But obviously also he did a lot of other work in dairy cattle in the Netherlands, but it's also sheep and beef in Australia. Because he just told me there's far more of them than the dairy cattle. And he's over here for a couple of days and giving a seminar on breeding for a changing climate.
Thank you, Roel.
Thank you.
It's great to be back here, especially when the weather is nice. What's better in Holland than nice weather? And I'm impressed about the university because it's all very lively, lots of people. When I left, it was almost collapsing, but since I've left, it's only gone up. So it's a good time. Yeah, so I'm going to talk about our work on breeding for low methane livestock. And I put sheep because most of my projects are sheep. I don't actually know a lot about sheep, but I always happen to have the sheep projects. And we have quite a lot of funding. And I might show the next slide. Can everybody hear me, or is there a microphone here?
I think it should be okay.
Okay.
Can the people online hear Julius?
Can you hear me?
Yes, everything working well.
Excellent. So in Armadale is a bit we do a lot of the genetics in Australia, except for the dairy. So I'm not going to talk much about dairy. You know more about dairy than I do. We do all the beef and the sheep, and my colleague Sam Clark does most of the beef projects in methane, and I do the sheep projects. So overall in Australia, our government is not some kind of Trump thing. It's quite forward-thinking and it wants to apply Paris agreements, and we have to all reduce methane by at least half it by some time and get rid of it by some other time. But really, every sector has to contribute to it. So they invested quite a bit in money to help us to see if we can reduce methane outputs in livestock. And a lot of the funding for the genetics is actually coming from Meat and Livestock Australia. A lot of funding for the feed additive stuff is more from the federal government, and we tap in both worlds a bit. So we have about 1.5 million dairy cattle, or maybe 2 if you count all the young stock. But we have 225 million beef cattle, so we have a lot more beef cattle, but we have also 70 million sheep. So for all the emissions in Australia, of livestock. Livestock is about 70% of agriculture. The beef cattle is about 2/3, so well, dairy maybe 5 to 10%, and sheep is about 1/3. So it's and roughly a sheep is 10 times smaller than a beef cow, but we have 2 to 3 times more of them, so that's about half of the emission. So sheep is very important, and so we want to work on it. And again, there's 2 ways to work on it. One is feed additives, and actually I coordinate a project funded by the federal government to look at how can you reduce methane with feed additives, and how can you make it practical for people to use it. And I also do that genetic selection program. So in Armidale, we're actually quite well equipped with material. So those are respiration chambers for sheep, and we have similar large numbers of respiration chambers for cattle. Declan is one of the biggest in the world, but it's the least biggest in the southern hemisphere. But I think we have about 12 for cattle, and we talk about maybe making it bigger. Those are mostly used for those feeding trials to see what's the effect of feeding seaweed or a bovaer or whatever to cattle or sheep. But of course, they can also be used for genetics if you want. But they certainly can be used for validating genetic equipment that we use, like green feeds or sniffers or what you have, because this is really the gold standard. You have an animal in there about 24 hours on a day, and you can really repeatedly. And so during the day, you also see a bit how much methane they produce every minute. So this is just a slide from experiment, and we compared if you give feed additives more often in the day, you reduce it a lot more. But even if you didn't give it, they have a bit of an eating pattern and a methane emission pattern that's relevant, especially if you collect data, what I'm going to talk later, at a certain spot of the day. It's good to know whether that pattern of the day matters or not. And in a way, the green feed data in beef cattle is also corrected for that daily, what you call a diurnal pattern, so that you get more comparable phenotypes. I'm going to stop about feed additives soon, but this is a slide that shows that they can really have a massive impact. So this is Asparagopsis, which is better known as seaweed, maybe. And they can really, if you give a lot of the times a day those pellets with the seaweed in it, you can really reduce methane by 88%. So in the short term, that's really a good way to use methane in livestock. But you have to do it frequently, and our livestock are not intensive livestock. They graze in the paddock the whole time. So it's a bit like what you see behind the screen. Extensive land where animals graze on land that can't be used a lot for other productivity. But how do you give those feed additives to animals in those circumstances? So that's a bit of a challenge. They wouldn't come all the time and always eat it. And some don't go to whatever dispenser you have. So it's still a challenge to make this practical and widely adopted. And it's also a challenge because it's quite costly. And why would people spend money on something that's not rewarded? So feed additives looks maybe nice, but it's a long term probably not great for cost, and on the short term a bit hard for getting that adopted. So this is what we found if you have those green feeds. So those are green feeds for sheep and paddocks. If you give them quite a lot and they have access to those, you could reduce methane quite a lot. Again, of course, a commercial farmer doesn't have green feeds; they're way too expensive. So you need some other way to feed them those treated pellets. So feed additives is a bit cost prohibitive and not that practical. But our projects try to look at, can you put stuff in water maybe? And so we also work with bovaer and other things. The problem is seaweed is also there's bromoform, and we suspect a bit that bromoform is not very popular, certainly in Europe. So you have to be careful. And I think the public perception about feed additives might not be great. So let's go to the genetic solution. So my project is called Selecting for More Methane Efficient Sheep, as opposed to Sam's project, which is called Selecting for Low Methane Cattle. And my talk is a bit about if we measure methane, what are we actually going to do in terms of selection? Do we want animals that produce less methane per head, or do we want something else? And if you say low methane animals, then you imagine that we're reducing the methane output per animal. But in my examples, that's actually not the best strategy. So a lot of this talk is about how do you want to select on a trait like methane? So the plan that we had, and it's similar to everywhere, I think, with genomic selection, we can select for new traits that nobody measures by making a reference population. And then with DNA testing, people can select for those traits. So this is a project that started 3 years ago, and it's almost finished. And we were supposed to measure 10,000 sheep for methane production and about 5,000 for feed intake. And then the good part of this proposal was also that we can immediately deliver those breeding values to the sheep genetics breeding value system. It's kind of a national database that provides breeding values for sheep to farmers. And we had used that same practice before. Like 10 years ago, we had a big research project on eating quality, so the IMF percent and the tenderness of the lamb meat, because if you select for animals that grow fast, the meat quality goes backward. And so eating quality is a difficult trait to measure, but with genomics and setting up reference population, you can select for new traits, and they've really changed the way they select for animals now. So it was a nice model that we could use for methane, just measure lots of animals and use breeding values. I won't go in a lot of detail about the fact that we also have different breeds and all that, because of course that matters as well. But most of our animals are merinos, and certainly the animals that run the whole year in the paddocks are merinos mostly. So that was our main target. So the way we measure that is in those boxes. So we call those packs or portable accumulation chambers. So it's a Perspex box of about, well, as you can see, the sheep just fits in it, and we keep them in there for about 45 minutes. And that system is quite portable, so you can fold the boxes and go to a farm and measure them. So our reference population for 35% exists of animals that we have at our university farm, because we run another project to measure those eating quality traits on a whole bunch of lambs. So if they go to the other project, we also measure them for methane, because the idea was we only measure animals that have a lot of other information on other traits, so we can estimate correlations with other traits very quickly. You probably don't know what MLP is, but it's a project where also we measure lots of traits like fertility on sheep, so those are used. But the important thing is we also went to breeders to make them aware of those traits and also to help them collect data on their animals. So we had an expression of interest. Who wants their animals measured? And then they say me. So we go there with a truck. Personally, I've never been there, but we go there with a truck and measure their animals. And that's like 5,000 are actually from breeders. And that's important for industry engagement. So that's because we want quick impact. And those are the people we discuss now also, like how do we going to select for them? So we haven't done feed intake a lot. So those feeders you see here are actually pig feeders. So recently we turned them into sheep feeders, and that works quite well. And the good thing of that system is you can also put it on a truck and go to a commercial breeder to say, we can measure your animals. Would you be willing to help? And so for the long term, when you want to maintain those reference populations, it's important you have a system where you can keep on phenotyping animals and people can co-invest. So you don't always have big projects from the government, but if people are interested in those traits, they can co-invest in it. And that's a way to keep data flowing. So for feed intake, we actually are building this in Armadale now. It should be ready next month or so, that you can measure 300 animals at the same time. But we're a bit excited about this feed intake system here. And also, this is a trailer which is similar to that, but you can use that to go to breeders. So the two pictures on the left are what we call mobile systems. And because think about it, if you have a system on your research farm, you can only measure animals on your research farm, but you can never measure commercial animals because people don't bring animals to your farm. That's for biosecurity, not a good idea. So mobile systems are quite useful. We don't have great experience with that system. We bought it in New Zealand, and I think they have it in Norway as well. The problem in Australia, it's just quickly too hot. So when you have metal chambers, not such a good idea. So, but in a way, the other one is also mobile. Okay, so a few words about, so if you measure a trait like that, it's important to know it's the right trait. So you work with sniffers a lot, and we work in beef cattle green feeds. Those are terribly expensive, so you spend already $3 million on to buy 20 green feeds or so. So those packs in sheep are good because they're relatively very cheap and they probably do well. How well they do is shown by the heritability, which is about 0.2, which we expected from the start. But as I said before, the gold standard is a bit the accumulation chamber, or the respiration chamber. So we're planning to compare those a bit as well. But at the end of the day, for breeding, you just need to rank the animals, and if they're all having the same environment in that contemporary group, then that's kind of good enough. However, you have a bit of a problem with how much methane you spit out depends a lot on what you eat. And in a dairy system here, when you have total mixed ration, that's quite similar. But if you have extensive systems that could be varying quite a lot, so sometimes it's very dry and there's very crap feed and it's all very hard to digest, and then you produce a lot more methane, and then you have fresh grass. So if you go around with your trailer to measure methane, and some properties there would be a lot higher average than others, and not only the average, but also the variation would be a lot. So it's important to standardize that data. So we do that for genetic evaluation, and we correct for, of course, for different between contemporary groups, but also for the variances. And we also tried to get a protocol for measuring a bit more tight, that before they go into that box, they have to be at least 1 hour of feed. And before that, they have to have a certain quality of feed available. Because if you don't have a bit of a protocol, you get a bit of traits measured all over the place. They might be very heterogeneous in what they are, what genes are behind it. And so it's important to have the right phenotype a bit more measured according to protocol. But as I said earlier, at the end of the day, what matters is what's the heritability, because that's a good, if you have crap data, you have a crap heritability, and it's about 0.2. So our trait is methane milliliters per minute, and we calculate it from that box because you know how the concentrations goes up in 45 minutes, and you know the volume of the box and the volume of the animal. So from that you can derive how much methane they must have produced. So in a way that's a bit easier than sniffers, where it's a bit of a guess how much you produce per minute, because you have to derive it from the concentration of air that's not controlled. Okay. Those flocks are different breeders we looked at, or different times we measured, and what we did is to see how well can we predict a group of animals. So we have, say, 10,000 in the reference, actually only 5,000 for this exercise. I think Michael Aldridge does this work for us. He works at ABU. You'll probably know Michael. But we take a subsample out, predict it, and then see how well it correlates with phenotype. And we found on average not too bad. So on average about 0.335 accuracy, but it varied quite a bit. And it could be, there's two reasons why some flocks are hard to predict. Here you see this one, it worked very well. Of course, one is a bit the sample size not very large of the test set. But the other reason is they could be a bit off in terms of protocol, like if they are really different in the diet they had on the day before they were measured, that could be quite different. But probably the main one is our population is not terribly linked always. Unlike Holstein cattle, where all animals have the same genetic background, in sheep you could be quite unlinked to the mainstream population, and we can't predict your genomically very well. So we're looking a bit at easy ways to measure that linkage as well. So if we do predictions, we know how reliable those are. It's quite an important part in the sheep industry. So those last week we gave breeding values to those people that we have measured, and we plan to release proper breeding values later this year. But the question is really, okay, now we have EBVs for methane, what are we going to do about it? And I show just this picture on the left is of a breeder that, so we gave them a spreadsheet. So those are your EBVs for methane, those are your EBVs for all the other traits. So of course you can quickly see, well, how does it line up? Are my best animals also good for methane. So on the left, there is post-weaning body weight is an important for lamb production. Like how much do you weigh after 6 or 7 months? And you see that the correlation is quite positive. In other words, those animals that you would want to select for productivity are also the animals that produce a lot of methane. There's of course a few outliers, but I mean that's what an individual breeder would observe. Like productive animals produce more methane. On the left, there's a correlation with overall index, which is productivity traits as well as reproduction and how many lambs you produce. And the left is a bit based on modeling rather than observation. But what we will see in the lamb industry is that productive animals will produce more methane. Yeah, so the correlation is about 0.5. And productive means you grow fast, but it also means you produce a lot of lambs. Because as opposed to a lot of cattle work, sheep can have 1 lamb or 2 lambs, but it matters a lot. If you need to produce 1 million tons of lamb meat, you can do that with half the number of ewes. Of course, you save a lot of methane because a lamb only lives like 6 or 7 months a year. But the ewe that produces the lamb sits there the whole year to spit out methane. So reproductive traits are much more important in sheep than in cattle, I think, because it means you need less mothers to produce the products that you want. I haven't looked a lot at wool production here. Because, of course, those ewes produce also wool, but it's a bit less relevant at the moment. So what is the best way to select for it? And so the aim is to produce less methane as an industry. Maybe not less methane per animal, we don't know. Let's have a look at what's possible. And I compare this a lot with selecting for feed intake. If people say they want feed efficiency, that means that for the amount of milk that we produce, we want actually to reduce the amount of feed that we need to do so. That's generally a bit the objective of animal breeding programs, that with fewer resources, we produce more output. And in a way, methane is the same. It's a costly resource. Methane is not good for us. So if we can produce more product with less methane, that's a good idea. So that's why I use the term methane efficiency. And so with feed intake, we have also different ways to measure that. So we just measure feed intake and production, or we don't measure, we calculate residual feed intake and production. But of course, those are identical ways to approach things. Or we can have those ratio traits like feed efficiency or feed conversion rate. Now, in the pig and poultry industry, they like those ratio traits. I think the cattle industry will like more the linear traits, and I would think it's generally a better idea. But do you select for animals to eat less? Like, do you select for animals that produce less methane? No, we don't select for animals that eat less, because animals that eat less are less productive, and it would actually decrease feed efficiency rather than increase it. So I looked at that. Yeah, so in other words, with methane, are we going to eat sheep that produce less methane per head, or for you have 100 animals? You want to have a breeding program that next year you have less methane than this year? And I would guess not, because you would also have less productivity. So what I compared is what if we selected just for profit per animal, as we do now, but then you can include methane and also feed intake additionally in the index and give a carbon price on it. I don't know if you have a carbon price here. We say about $40, $50 per ton of CO2. And that actually doesn't do a lot. But anyway, you can put a carbon price and see where you go. You can also select just single trait methane per head downwards. Like we want animals that produce less methane. Of course, not realistic, but let's see what happens. And you can also select for methane intensity or methane yield. So the New Zealand is like methane yield, which is how much methane do you produce per kilo of feed. And I always wondered a bit why they do that, but I think the answer is they want an industry that doesn't use less land. So they don't want animals that eat that are more efficient, because they want to keep the total land used for sheep production in New Zealand, they want to keep constant. So if that's the constant, then you have to reduce methane for the amount of feed that you have available in your land. So how that compares with the others, we're going to see in a minute. I think amount of methane per kilo of lamb, so methane intensity is a relevant thing because at the end of the day, why do you have an animal production system that produces output? And for a given amount of output, you want to reduce the amount of methane. So I did some selection index work just to compare those strategies. But this, I don't propose to have a methane intensity as a trait to select on. I propose it as an objective target, similar to profit is a target. Like you want to select on traits such that your profit increases. You can also select on traits such that your methane intensity improves. So, to do some modeling, I used first some parameters, and they're very important to have correct, and we can do some sensitivity analysis. We had a reasonable idea of traits, so I just summarized the trait, but it's basically post-weaning weight is how fast you grow, and that's how you sell lambs. Adult weight is important for the ewe running around in the paddock the whole year. And fertility and litter size are two traits related to how much lambs does you produce per year, because that's going to be an important impact of how many ewes do you need to produce lamb. And then feed intake and methane are additional traits that we have to measure, but there's been quite high correlation between them. And I think here you find much lower correlation, so that's a bit interesting. I also assumed a heritability of 0.2 so many years ago, which happens to be a good assumption we see now. But that correlation with feed intake and other productivity traits are going to be important to estimate. But anyway, those assumptions that I have in my modeling are not too far off from some historic stuff that we've seen. The other thing you have to assume is how accurate can you select for traits, because where you go in your breeding program depends on accuracy of traits. So with genomic selection, I assumed that those traits could be predicted with about 30% accuracy, which is not terribly high, but at the moment probably not unrealistic. And you can also do modeling what if that was 0.5 or 0.6, but let's start where we are now. So I did basically selection index work, added those two traits, calculated weightings for the index based on different objectives of your breeding program. I assumed genomic selection and predict response to selection. So I did not use ratio traits, I used traits themselves. So I did not select on methane intensity, I had methane intensity as a goal in one of the strategies. So those are the weights. So if you select on profit, those are the weights that you use for the traits. However, those are not expressed as dollars per unit of the trait. They're expressed as dollars per genetic standard deviation, because that gives an idea of how important that trait is relative to others in how much weighting they really get in the index. You know, otherwise, it depends on the unit of measure. So if you select it for, so just to be clear, if you select for profit, we get a negative for daily feed intake because feed is a cost. We also get a negative for methane production because methane had a cost in my modeling because of the carbon price. If you select for methane per head, so you didn't worry about productivity, just I want to reduce methane, you get only weights for methane itself, but also for the fertility traits. The other traits will affect methane, but that's through the correlation. But the weights that you have in the index should not be driven by the correlation between traits. They should be driven by the first derivative of the equation of your objective function. And fertility has a non-zero value there, again, because in the production system, the ratio between ewes and lambs changes fertility. And that's not a genetic correlation thing, that's a production system thing. So that's why those traits are weights. If you want to improve methane intensity, you get weightings for how fast you grow, for fertility. They're all positive because the faster you grow, the more lamb you produce, and the more fertility, the more lamb you produce. You still have a negative weighting for methane here. So let's see what you kind of responses you get. So I've put quite a few numbers on, but roughly, so slaughter weight is the key trait for lamb production. So those are the means, those are the changes you get, and that's the value of those changes. And so most traits contribute to more profit per year. At the end of the day, I predict $4 more profit per year is your rate of genetic change. A lot of that comes from more growth, some of it comes from more fertility, And that's of course a cost because you're going to eat more. You're not going to eat less because you produce more. But also you're going to produce more methane because methane has a positive correlation with all those production traits. So that has a small negative response, but methane is not terribly important, as you can see here also on the relative weights. You kind of can compare economic value of trade with this number here. And a carbon price of $40 is not terribly important to give methane a lot of push. But the important thing is that, so although methane still goes up as a correlated response to productivity, the methane intensity goes down a lot. So per year, methane might go up by 0.7%, but and the total flock a bit more because you produce more lambs, they also produce more methane. But the methane intensity, so the amount of methane we use per kilo of lamb that's sold, is actually going down by 2.6% per year, which is quite considerable. So I think this should be an ultimate goal. So at the individual trade level, you don't see those changes, but due to the system interactions of trades, you get quite a large reduction in methane intensity, which is good news. But it's hard to sell to people a breeding program that says your animal is going to produce more methane. The fact that it's more productive is often hard to understand. So if you reduce methane per head, so you select animals that produce less methane, and you certainly have a selection response of 1.25% per year. That doesn't have a lot of value, but anyway, the purpose is not profit, the purpose is methane per head. But they're also going to eat less, they're going to produce less, they're going to have less lambs. So your methane intensity goes up 2.5% rather than down 2.5%. So it's not good to select for animals that produce less methane in the sheep industry. So I just had a discussion of this rule. Apparently in the dairy industry here, it's not as extreme, like the correlation with the index is not 0.5 as in this modeling, it's more like close to 0 maybe. And then of course you have less that problem, but still you have to choose between profit and methane to some extent. So if you select it for just methane intensity, that's the maximum amount of intensity change you can achieve. And that goes a bit to the expense of the profit genetic progress, but about 20 or 30%. So you still, but the point is a bit that most of the methane intensity gain is to profitability rather than reducing methane. So I looked at that as well. What proportion of the improved intensity is due to what trait change? And most of it is due to weight. It has quite a high heritability and can change a lot. Quite a bit to lambing fertility improvement. And methane has a negative effect because that still goes up, and it has, of course, negative effect. But that effect is much smaller than this one. So the conclusion of all that is productivity improvement contribute quite a lot to improving methane intensity. So in other words, what we're doing at the moment, without measuring methane, we're already improving methane intensity because we have more productive animals. Let's see, this is methane yield, which is Peter Amer's hobby thing. And I don't think it's such a great idea because you reduce methane intensity a bit, but not as much as you could if you just selected on profit. But you get, so I'll have to have a discussion with Peter Amer what he thinks why that is a good idea. I don't know if do you talk about methane yield in cattle at all or not? No, it's maybe a New Zealand thing coming out of Abacus.
Beef cattle, sometimes you talk about it, it's methane per kilogram biomass intake.
Yeah. So that's where that comes from. But why that would be an objective of your breeding program, I'm not convinced about that. Okay, so this is kind of the same slide about the 4 strategies, just clearly showing that you earn a lot in the productivity traits earned, and also if you put a bit more emphasis on methane, both to productivity and reproductivity, you lose a bit, of course, to animals eating more, and you lose very tiny bit, and they just produce more methane. You can push methane a bit harder by giving a harder weighting to it, but it will always go a bit to the expense of productivity. And so I wouldn't focus too much on methane per head. I would focus on intensity. but at the end of the day, a realistic breeding program will have to weigh profit and methane in a certain way, and I'll look at that in a minute. When I talked to Rob Banks, who's kind of helping with the global methane hub, he still had a lot of problems with this methane going up per animal, because how do you sell that to the funders and the general public that if animals produce more methane, that's not good for the environment, whatever way you look at it. But of course, what should happen if animals are more productive and you have produced the same, that you have fewer animals to produce that product, and that's where the gain comes from. So I looked a bit at a national level, and it's a bit small letters maybe, but just currently we have about 35 million breeding ewes in Australia. So we have 70,000 head of sheep, but half of them is breeding ewes and the others are lambs and young replacement stock and all that. They produce so much lamb, they produce so much wool, they eat so much, and they produce less methane. So if we kept the same number of animals, so we didn't change the size of the national flock, if you select for profit per head, we would actually, almost double the amount of lamb we could produce, but we also get a lot more methane. But as you can see, the ratio between product and methane is actually improving. So, but of course, the environment only worries about how much we spit out. And you could argue that's not a good strategy, because after 20 years, so this is 20-year response, you have more methane and we want less. We should at least halve it. We could halve it if we selected for meat against methane per head, but we don't have any product anymore. So is that what we want? Or if we select it on methane intensity alone, we also get more methane and a lot more product. So where are we going to go? So then I thought, well, suppose the government says we have now 15 megatons of CO2 equivalent, so you have to reduce it by 30% or half it or whatever. So I did here 30%. So the number of ewes we would need to produce the lambs for the meat, would have to go down from 35 to 23 million. So here we generally have less methane from the sheep industry with more productive animals. So we need a lot fewer of them to produce kind of a similar amount of product. And of course, the more they restrict the industry to produce methane, the less product we can have. But this is still a pretty good percentage of what we have now. If we selected for profit, this is if we didn't select. This is if we select for profitability, so then we can maintain the same total amount of output with less methane. If we selected for methane per head, we would need more animals to do that, and we would have no product because we would have very unproductive animals. And if we selected for methane intensity, it's a bit similar to profit. It's quite correlated, but we would even have more product out. So it's important to look at the best strategy has to be related to how the future industry looks like in terms of what comes out and what goes in. And we shouldn't be stuck to a fixed number of animals. And we've had the same here. Like, we have a lot fewer dairy cows than we had a few decades ago, but they produce overall the same milk or maybe more. And so that means that overall we need less resources and less methane to produce that amount of milk. Okay, going back to finding the right index. So I'm a fan of the ellipse. So the ellipse is always, if you have two traits, you can change them any way you want according to that ellipse here. So, and it's mostly relevant if you have two traits that have an unfavorable correlation. So in our case, the two traits are all the other traits together, which is index, so that's dollar profitability basically. And the other trait is methane. So if you just select it on animals that produce less methane, you have to have those animals. The more you select for it, the more you go down in your response for index, because there's that negative correlation. And as a matter of fact, the size of that ellipse is a bit hanging forward. That's because it's a positive correlation, but it's the correlation between the estimated breeding routes. It's not the correlation between the traits. Yeah, so if you had more information, that ellipse might change, even though the correlations might not change. But with the current numbers, you would select the response that we saw earlier, basically looks like this. So you select for the best animals according to this. This trait didn't have a lot of, so according to index, this trait didn't have a lot of relative weighting. So on average, you go a bit up, 0.16, and this is the amount of change you can achieve. If you say, no, that's not good enough, you need a bit less methane, you could increase the carbon price to give more weight to breeding values for methane, but you lose a bit here, of course. So earlier we had 4.3, and now we go back to 3.7. But the positive response for methane that we had here is now reduced to a almost zero response. So it's kind of a restricted index. So a selection index, you can play around with what if we restrict the response to a certain amount, what do we lose in the other traits? And if you have a higher carbon price, then more and more you can actually reduce methane, but you see then you lose quickly a lot more. So the ellipse picture is very insightful because it shows a bit how you move according to that line and where you really fall down a lot. So you don't want to probably put so much weighting on it because then you lose too much here. You want to sit a bit more at the top. Yeah, and so again, ellipses are used for 2 traits, but they can be used for multiple traits as long as all the other traits versus methane. That's basically the problem that we have to solve. And it's good to remember that with multi-trait selection, your response depends on the weighting you give to your traits, but it also depends on the accuracy and ultimately the correlation between the breeding values, not the genetic correlation. And so you can choose the weighting, but you can also determine what you measure in order to manipulate where you go. And so, because the next question is, do we need to measure methane? Because we already improved intensity anyway. What's the value of additionally measuring the trait? This is similar to saying, we want to improve feed efficiency. We do it already by selecting on growth. What is the added value to also measure such an expensive to measure trait? And so that's what I looked here at. And basically, come back to this, but what you do is, if you compare those 2 slides, if you didn't measure methane, then that ellipse becomes much thinner because the EBV of methane would depend on the correlation with the other traits. And if you have less information, you have less leeway to optimize that optimal response. So I'm trying to show that here. If you so carbon price is kind of how much weight you give to the trait in the index, but measured versus not measured is determining the size of the ellipse. Yeah, again, that ellipse is really the correlation between EBVs. If you do not measure a trait, an EBV relies more on the correlation with other traits, and the correlation between EBVs becomes much tighter. So if you did measure methane, you could keep it at 0 and still have a reasonable response. But if you did not measure it for the same weighting, you would always go up for that response. And it then seeks a response for the trait you have measured, but it goes to the expense of the ones you have not. So if you put a bit more weighting on methane, you have that's a similar problem. But if you then want to, so if you do not measure it and you want methane not to go up, you lose a lot of productivity. And if here you have more ability to reduce methane to really balance the 2 traits. I made this example very quickly in the last 20 minutes. I should probably have a better example, but it really refers to the fact that if you did not measure a trait, the correlation of EBV with index becomes high because it depends on the correlation with the other traits, and then it's harder to find a good point at that ellipse where methane doesn't go up too much because very quickly you slide down to losing a lot of profit. So it's good to show those options to people to see how much emphasis do they put on that breeding value. So in summary, we try to reduce emissions mostly at the moment already to more productivity and reproductivity, and certainly in sheep. But of course, we need to do a similar exercise for beef cattle and for dairy cattle to see how that fits. And maybe Anouk can comment on that. I think she did already in her thesis. But we get EBVs out this year for the industry, and we need to give people advice and how to select for it and whether to put in the index and what kind of response they expect. So I think our plan is to just show them clearly those options they have, because otherwise they have no idea what to do with that information. So, and in that discussion we have to have is really, what is your target? Do we all agree that we need a methane intensity times of target or something else? But we have to be aware of the consequences of different ways we do it. The trait definition is still quite important, and also the phenotypes to compare them is of course always an important aspect of any breeding program. Index weight depends on what you want and what information you have. And I suppose the last problem is a bit, what is the incentive of the industry to maybe sacrifice a bit of profit in order to have less methane as an industry? But our sea breeders are actually extremely progressive. Like a decade ago, they all selected for better eating quality, although nobody was paid for it. But we all imagined that someday we will be paid for it. And as an industry, they really often take that responsibility. And our breeders are really keen to use breeding values. So Australia is a good place to immediately turn this research into impact. And I think that was the end of my story.
Thank you. Questions for Julius?
Yeah, so you are opting for that we need to keep improving production as well, but then you show also that that means that we would need to have a cap on methane maybe to reach climate goals, which means keeping less animals. On the Netherlands, we're now having these kinds of discussion more related to nitrogen, that we have to keep less animals, but that results in a lot of like resistance from farmers and also the industry. How do you see that happening in Australia? What are the trends now for sheep and beef? Is it increasing still or already decreasing?
Yeah, we don't have the nitrogen discussion so much, but I would say, like in your case, like what I learned from my exercise is it's not just a selection index exercise, it's an exercise where you link the selection index modeling to the systems modeling, like what happens, and then decide what to do. But we don't know yet what the levers are of the government to reduce methane. Are they going to force us? And how are they going to force us? Can they measure methane? And like that incentive pattern is important for how they will respond. But again, they tend to be quite responsible themselves. Even they don't want to lose too much money, but they also want to have a clean industry for public perception. I think there's lots of supply chains that want to buy land that is low methane because the supermarkets push it, and I think you also have your milk companies that push you on low methane. So there's several actions that drive a certain way how the industry evolves, I think. And best we can do is to see if we can put it in models, and if there's constraints on numbers, then that can be easily put in a system. So I believe that's the best way forward to see what is the best strategy. But it's important also to avoid uninformed discussion. Like people talk about different things while they think it's the same, but actually they don't understand each other. So you need to be clear on the definition of the trade. You need to be clear on the definition of the objective.
Yeah.
So you just talked about the government restricting the numbers, right? But what would be the autonomous development of numbers of ewes or and lambs if you start selecting for productivity? Because you then because you mentioned that the number of ewes is really determined by the grazing of the land. There's a requirement for that the land is grazed, right? But there's also market flexibility.
Yeah.
On the amount of lamb it can absorb, right?
Yeah.
Otherwise, before the prices drop and it becomes not unprofitable.
Well, I think 20 years ago, when it came to Australia, they had twice as many sheep, like 160,000 million or so. Since I'm there, they reduced it by half. I have a lot of influence on it. That's mostly the wool industry, so the wool has gone down a lot, and it's hard. But you're right, it's totally the markets that drive it. And with methane, it's always the question, like, should Australia just produce the lamb because they're efficient and they're big and relatively it's a good system, and then other people can stop producing lamb? Or, like, there's always difficult discussion. I think it's best yeah, it's hard to predict. I think what is the best way, but I mean, in all the scenarios, more productivity is usually the best way to move forward. It's always it doesn't go to the expense of the animals, of course, because it's always that principle is always based on using less resources for an output that you need. And the whole discussion about being objectives and being economic values, like Braskamp and Charlie Smith, and that was always the line of thinking, I think.
Yeah, but the industry is interested in reducing the total amount of methane produced, right, for this whole sector.
Yeah.
So if you produce, if you improve productivity, you
Or you can
you keep the total amount of land produced constant, right? Then your total amount, even though per animal it increases, for the sector it decreases. So that should be the justification of that way, but only if the total amount of land produced remains constant. It was not in your scenarios.
well, sorry, what you want to produce the same output?
Yeah.
And then have a breeding system such that, so if you select for less methane per animal, you have less methane to produce the same lambs. Actually, I think the best way is to look at this one.
Now you use your profit
This one?
option, yeah, and the profit per head. If you reduce the number of ewes, because here you keep it constant at 35 million.
Yeah.
But if you reduce it proportionally so that the total amount of land produced is the same, because you double it almost here, right? So if you reduce it to 665,000 tons, then your total the CO2 equivalent really drop for the same amount of land produced, and that's what you want to achieve, right, for a sector.
But is it not so? Sorry. Yeah. So here we produce the same amount of land as here, but there's a lot fewer animals, so we have a lot less methane.
Yeah. Okay. So that's in the same direction. Yeah, that's right.
Yeah.
Yeah. That's what. Yeah. Okay. But if people only keep the ewe flock on the number of ewes per land, right? Then
yeah. So here I need a lot less land, like less feed, so we can put houses on land rather than give lots of space. But that's why. I mean, the economy works such that if you do most profitable, then you have the most overall utility. So you can use land for other purposes sometimes. We can use it for nature. We need more nature as well. You need certainly more nature.
It's very, very clear, and we need the numbers to have an informed discussion. The disadvantage of this message is that we as animal breeders have the habit, if we keep on doing what we always did, select for productivity, we always do best. We had the same discussion when it was about health traits. If the cows give a lot of health or give a lot of milk, then the health is okay. So, how do you find to tell the story?
Yeah. Well, I mean, a few examples of those are good, but sorry. I mean, this is also useful, I think, to see, look, given the parameters that we have, which direction do we want to go? Do we want to go to the right, to the left, to the bottom, or the top? And those are the options we have, right? You can only see options. We are not deciders, we are option providers.
Yes.
Basically, you come to the same conclusion: less animals is less methane, right? And that's also what the environmental people like. We need to cut down the amount of animals.
Fewer animals are the more productive.
Yeah, and then
if they're
maintain that production.
I think in animal production there will be discussion about productivity also a bit like in dairy. Like, do we still want animals that produce 20,000 liters of milk, and is that good for the animal? So that's of course a restriction we might have as well. We don't, not so much in this production system, I think.
But the number of lambs can also be an issue, right?
Well, they don't have a lot of trouble having twins.
No, but you don't want more than.
No, that's right. Ultimate damage. But we're way behind. New Zealand is much further than that. But like, I think you said that your correlation, your ellipse is more round, right? Yeah. But even if it's round, you still have you still have a bit like, do I go here or do I go here or do I go here, right? So if you go against methane, go less for profitability. If it's perfectly uncorrelated and you select only against methane, you don't get any productivity increase. So, and breeders are not paid for, or producers are not paid for methane at the moment or penalized for it. So why would they want to give up productivity? So I think we need some kind of balance.
Yeah, it stresses the need to do the sums and to investigate it rather than just talk. So, are there any questions online?
Question. Oh, you mentioned that the accuracy of breeding values obviously is relevant, but in this context, with all the different traits that you look into, how useful is it to try and increase that accuracy? Is that how to achieve the goals or not really?
Yeah, no, if you increase accuracy, I mean, there's two ways you show the table. I think I have a slide somewhere. I did that exercise in the table. But like here, if you increase accuracy, that ellipse goes just further away, and if you increase accuracy in an equal way, like some traits more than others, then the change of the size of the ellipse. Again, it's good to realize that where you can go is determined by the ellipse. Is purely a function of the variance covariance matrix of the EBVs. Yeah, and of course, a bit of variations in population, but and with genomics, it's a bit less so. Everybody has accuracy in its own prediction that counts, and the correlation between genomically predicted breeding values. So we can pretty well predict where we go if we know the covariance matrix. So where we go then depends on that line, which is the slope of the economic value ratio, right? So the more, so I use it always for multi-trait selection lectures, that the slope of that line is a ratio of the weights, economic weights. The ellipse is where you can go in a certain amount of time, and where the slope touches the ellipse is the optimal index solution. So if you change the weights, then you can see how much do you have to change the weights to go from there to there in your response.
Yeah, a bit different question. I wondered if there is any genotype by environment interaction, because you mentioned the feed has quite a lot of influence.
Definitely, well, I'm not sure interaction. Interaction means the ranking change. So definitely a big effect on the diet, on how much methane you produce. But equally, there's a big effect on diet on how fast you grow, right? So we account for contemporary group differences and assume that the trait is the same. But it would be useful if you have really different systems to always check whether the traits are the same traits genetically as well. But I think in first instance, you have to assume they are. And if you have lots of data, you can ask questions like that.
Maybe it's more common, but I heard a presentation from DSM about bovine, and they had to do trials in 80 countries to become a registered additive to be allowed to feed, and they have to build 2 factories. Then I was thinking, okay, animal breeding companies complain about phenotyping 15,000 animals or something. Obviously, the profit margins are far less, but if you then see how easy it is for animal breeding, you start recording, do genomic prediction, and you can start. But if I saw all the effort they needed to do to get bovine introduced in all these countries, it was really impressive.
But what I showed in terms of response after 20 years, right? So it still takes a while before we actually have an impact on methane emissions.
Yeah.
When you use bovine tomorrow, I can reduce it by half at least. So it's too expensive probably, but it's quite a big difference in impact.
But you have very strong genetic correlations between. What was it? Productivity was.
Yeah, but I mean, any genetic change takes a long time before it happens. It's cheap and it builds on each other, and long term it's powerful, but short term it doesn't help reduce methane a lot. So you might have to work with a bit of both. Maybe.
Using those additives, there's no repercussions from that, or it doesn't.
No, we haven't.
What happens with the methane then?
Well, so what we do, so methane that is not spit out our hypothesis is you can use that. Then you need what we call a nitrate, and methane sink, which is nitrate because it can bind like proteins. Or I'm not a nutritionist, but I'm leading the project. But that's what I understand. So we use feed additives with nitrate and also vitamin A2 or so, whatever, to see if it also improves productivity and use it for productivity. And the argument is that if farmers see an advantage of using it because they also have more productivity, there's incentive to use.
Right.
And the other one is how can you cheaply provide it? So we play around with putting it in water, have to drink water, and then never really use it. So we're working quite a lot on having practical ways to provide additives. So we work mostly with Aspergopsis, which is seaweed. Now Bovair, there's Agalin, that's kind of a natural product that doesn't work so much. So I think, but how you measure methane is an overlapping thing. So we're also looking at better ways to do that. So you have your sniffers. Some people look at NIR methods in feces maybe to predict certain things. And if you have a platform where you measure lots of traits, you can test new ideas as well, right? Like how does it predict what you do? So that's quite an exciting area. But at the end, it's only useful if you have impact, right?
Okay. If there are no more questions, we thank Julius, not online. Hope I see the hands. Okay.
Okay. Thanks all.
Thank you very much, Julius.
I'll see you the next time.
Ja, nee, maar dat is ook heel is ook handig uit te leggen om na te denken.
Ja, ik